So in this video, we're going to go over another technique for solving Diophantine equations. And if you watch, I strongly recommend you to watch the factorization videos first, because I will assume that you guys would have watched those videos, because there are some things that I said there which you will have to know for this video. So remember in factorization 2, the video for factorization 2, we looked at difference of squares. We're going to look at sum of squares this time. And we always looked at, until now we just looked at like factorization. So like if we have an integer expression times an integer expression equals an integer, then we could reduce it into a finite number of cases where an integer times an integer equals an integer. And then we can just simultaneously solve them. And it was a really good technique. It was like sometimes, but like, I guess sometimes it felt like by exhaustion, like exhaustion of all the cases. But like, I guess there always exists a better solution, but sometimes this is the only solution you can really do. But yeah, it was a very useful technique though. It meant that if you can factorize an integer into two integer expressions, then you can always solve it in a finite amount of time. But in this video, we're not going to look at this. We're going to look at a relatively new technique. So I'm going to just give you the question first. And I'm going to test if you remember what we did in the previous videos. So I want you to put this. So remember okay, I'll just say. So remember the last video we just looked at, like if we have this kind of form. But we looked at minus y squared. We looked at minus y squared like this equals an integer. But what if we put it like, what if in this case it's in the form of plus y squared plus 2by equals integer? So in this case, if we add a squared and b squared to both sides, it's the same as this though. In this case, we added a squared and minus b squared, but in this case, we're going to add a squared and add b squared because we want to make this into a square plus a square. In this case, it will be a square minus a square, I guess. And plus a squared plus b squared on this side as well. And then it will just be x plus a squared plus y plus b squared equals that another integer, but it will be equal to this plus this plus this. So, so unlike this case where we could factorize it, unlike this case when it was like x plus a squared minus y plus b squared equals an integer, we could factorize this, but we can't factorize this. It's a sum of squares. So why are we looking at this technique? And this is because you'll see later, but we're going to look at a special case first, and then we're going to look at another problem that will clarify things a bit. So using this technique, we're going to factorize this. So we have x plus 1 squared. If we add, so we have to add 1, and we have to add 4. So we have to add 5 to this side. So this will be x plus 1 squared plus y minus 2 squared equals 0. So now what do? We can't factorize it and stuff, but realize that this side is equal to 0. And we always know that not just for integers, but for real numbers. We know that x and y are positive integers in this case, but the condition is that x and y have to be integers for all the problems we're going to do. So x and y are integers, so they're real numbers, and so these are real numbers. So these are squared of real numbers, which means that these are larger than or equal to 0. But they sum to 0, which means that they have to be equal to 0 because their smallest value is equal to 0. So but their sums are all equal to 0, which means that they all have to be equal to 0. So x plus 1 is equal to 0, y minus 2 is equal to 0. So x is equal to negative 1 and y is equal to 2. So even though we didn't factorize it, using our knowledge of like the boundings of bounding, we found out that they all have to be equal to 0. So x is equal to negative 1 and y is equal to 2. So you realize that even if x and y are not integers, even if it's not given this, if they're real numbers, even if they're just given as real numbers, then it will be the same because the squares of real numbers have to be larger than or equal to 0. So yeah, it's pretty interesting. It doesn't only apply to number theory, but also to algebra in general. So yeah, remember this common technique. If a sum of squares is equal to 0, then yes. So But now we're going to look at a case when this is not equal to 0. So what if, so in this case it was quite coincidental, or the maker of this problem intended it to equal to 0. But what if this set is not equal to 0? We want to be more flexible with these kind of problems. So I'm going to give you another problem, and this time I'm going to give you it in the form of already like expressed as the sum of two squares. So how do we solve this now? So now it's not 0 but 2. So how will we solve this? And now it becomes more specific to number theory. So that in this case we looked at it. It was open to real numbers as well. But here, if x and y are equal to integers, then we can solve this. So firstly observe that 2 is a very small number. 2 is a very small number. So these are all larger than or equal to 0 again, which means that we just have to find two positive integers that sum to 2, which is just 2, 0, 1, 1, and 0, 2. Okay, I'll just write them down. 0, 2, 1, 1, and 2, 0. But say that this number wasn't that big. I mean, in this case, 2 is very small, so... Okay, how should I explain this? Yeah, so... Okay, regardless of whether this number is small or not. So if this is a big number, then you will have to write down, it will take a long time to write down all the possible cases. But remember that these aren't just positive integers, non-negative integers. These are square integers. And square integers are very specific numbers. So it's only 1, 4, 9, 16, and so on. So they are very specific numbers. So there won't be so many cases. There won't be like a lot of ways to express a relatively not large number as a sum of two square integers. So in this case, only this one works, 1, 1. So x minus 1 is equal to plus minus 1, and y minus 1, y minus 11. Y minus 1 is equal to plus minus 1 as well. So and then you can solve it on your own. I'm too lazy to write it down. But the main takeaway from this is if this is a relatively small number, a really, really small integer, then just list down all the cases and then look at, oh, is it expressed as a pair of squares? And then, but if you get a relatively not large number, like, let's say, what is there? 65. So 65 is not a very large number. So it's a really subjective way to, it's really unclear to say that it's a relatively not large number, but you get what I mean. So like 1,250, like these are, yeah, these are very large numbers. But in this case, like 65, you can just think of all the all the square integers that are smaller than 65, which are, and then you list them down, and there are not that many, and then you realize this is equal to 49 plus 16. So it's like you can easily, for integers, you can really narrow it down. So that's why I really like number theory, because you should always be able to tell the difference aside from the integers, like aside from number theory being narrowed down into integers. It's not about, like, number theory is not a subset of algebra. You have so much more stuff you can do, because if you can narrow down the cases, then you can do so much more, which makes number theory actually, in my opinion, a bigger topic than algebra, to be honest. Yeah, so this was a new technique we looked at today aside from factorization. So I hope you enjoyed this video and hope to see you in my other videos.